We're going to be talking again about Hall's juggling theorem. Now, the last time we talked about Hall's juggling theorem, we talked about how the process works. In other words, we have a set of numbers whose average is a whole number, and how it can be rearranged to make a juggling pattern. But what we didn't talk about is why it works. So why does this algorithm always succeed? And it's not trivial. It's just not the case of like, oh, if I have an idea, it works. So there has to be something behind it. There's some math involved. And the math explains the why it works. So that's our goal for it now. So make sure that before you watch this, you go back and you get a good understanding and intuition of how the process works. So that's in the other video. Now our basic approach is going to be one where we use a technique called proof by contradiction. And to sort of motivate it, I'll tell you a little thing I used to do when I would teach a class. And what I would do is one day I'd bring in a big pile of donuts. Very good donuts too. And also a big pile of spinach. There's also good spinach too. You know, I don't shortchange my students. And then I would look for a volunteer, or well, someone would get voluntold to answer a question. And I would hold up 2 cards. And I'd say, okay, one of these cards has the word donut written on them, and the other card has the word spinach written on them. Now, you get to pick the card, and whichever card you pick, that's what the class will enjoy. So maybe the class will be enjoying donuts, which is usually considered favorable, or the class will be having some spinach, which not so much. And I said, okay, so you have to pick. But, and this was me being nice, I'm not going to tell you which one says donut, but I will tell you it's not this one. And then I would ask them to pick. And so sometimes they seemed confused that I was going out of my way to saying, I'm not telling you where it is, but I will tell you where it's not. It's not here. It's not this one. Have you figured out which one of these 2 says donut? Yeah, it's right there. Donut. And in case you're wondering, I'm not cheating. It does say spinach on it as well. So you might say, okay, well, what are you doing? What's the point of this little exercise? So what we're going to do is talk about this method. So suppose we're in a situation where we're trying to show something is true. Now, oftentimes, there's only 2 possibilities. It's true or it's false. You might say something like, it's A or it's not A. So it's like we've split into 2 cases. Now, what we want to do is we really want to say, hey, I want to show this is the truth. It's almost like I have 2 doors to pick. And I say, look, I want to show it's behind that door. Well, how can I do it? Well, what we can do is eliminate the other possibility. See, there are only 2 possibilities. So if I can knock one possibility out, that leaves me with just one possibility left, and I win. I know what to do. So how to eliminate? So this is the contradiction part coming in. It says, okay, well, let's for a second go in that direction. So in other words, we're going to assume that whatever it is we want to be true is actually not true. We're going to say, okay, suppose it's not true. Let's make an assumption of some sort. And now that we have our assumption, we say, okay, let's follow the logical conclusions forward until, lo and behold, we reach some kind of a paradox, an impossible situation. We say, well, wait a second, something is wrong. We've reached a contradiction of sorts. Now, when we say something is wrong, that means an assumption is wrong. Somewhere along the lines, we've assumed something which doesn't allow us to actually work. And we backtrack and say, oh, our assumption that we made was that A is not true. Well, so it must be the case that A is not true, or A is true. Okay, so that's sort of the idea. Is so proof by contradiction. Well, let's assume something is doing what we don't want it to do. Shall we reach some kind of impossible situation and say, aha, so it must be the case that it does what we do want it to do. All right, that's sort of the game plan of where we're going. That's the tool we're going to use to show that Hall's juggling theorem actually works. it probably is good to have a really quick recap of how the procedure works, because we're going to be running this process through and talking about how things move. And so if you can't remember, it's not going to work very well. So here it is very quickly. The idea is that we always take rooks and we're going to move them into the first available row. So we think about the rooks from top to bottom. We say, look, we're going to put rooks in the first available row. So I have a rook, and I say, okay, let me move it to the first row. And every rook, by the way, is associated with a number. And that number is where on the row we cover it. Okay, boom. Now, it could be the case that there's another rook already in that same column. Uh-oh. All right. Pick up the one that was the conflicting, not the one you just placed, but the one that was already there that caused the conflict. Pick it up, and now repeat that. Move it to the first available row, not the row it came from, but the first available row other than that, and put it down, and repeat, and repeat, and repeat. And we continue until there are no conflicts. And once we've done that, we've put the rook, and then we repeat that with the next rook, and the next rook, and so on and so forth. So really, what's the hard part? Well, really is this piece right here, the continue until no conflicts part. How do we know we actually reach that stage? So that's where we're going to be putting our energy in today. Now, just sort of to help us get some intuition, get a feel for it, let's make a quick observation. And this will be nice, just sort of to help us get our sort of mental picture of the process going. And it says the following. So when we take a rook out of a row, in the next step, the row will be filled. Now, let's just stop at that sentence. Why do we know that? Well, because once we take a rook out, that row becomes available. And in fact, it becomes, once the rook has been placed, it'll become the first available row. And remember, we always move into the first available row. So that's how we know it's true. We know it's true because of we move into the first available row. Now there's a second part. Moreover, when we put the rook, it will be in a different position. Okay, well, that one maybe is not quite so clear. So let's think about what's happening. All right, so what's happening here? I can imagine I have some rows, and let's sort of follow the procedure. And it's good to just sort of visualize what's happening. So I place a rook here. And now what happens is that there is a conflict somewhere else. So this is I place, and I'll put an arrow saying, conflict. Okay. So now this is the rook that we have to move. So that's the one we're taking out of a row. Now, where does it go? Well, it goes to the first available row. Now, that row might be above it, might be below. We don't know because, rows that are available move around. Well, let's for a moment suppose maybe it's above it. Okay, so what do we have? Well, it's going to move, and it has to cover the same label. Whatever the label was here, it has to cover the same label there. Now, there's a claim it's not directly above it. And why? Well, because all the labels in a column are distinct. And so if I'm moving to a new row, I have to move into a new column. So I've moved over into a new column. All right, well, great. Now, what's going to happen? Well, if our process is going to be continuing, we say, oh, well, wait a second. Maybe there's a new conflict. All right, so now I've moved into a new column, freed up that row, and I say, a new conflict has emerged, so now we have to move this one. Okay, and here's the second part of the claim. The second part of the claim says that, look, this is now an empty row. It's the first empty row, so we have to move back in. We can't move back where we were. Why not? Well, this has a label. So whatever the label is here matches the label there because the rooks maintain the labels. All right. Because these two rooks are in the same column and all the entries in a column have distinct labels, these two labels are distinct, which means that this label can't match that label. So when it goes back in, it goes back in somewhere new. Okay, so they're sort of like a couple steps in the procedure. And that's the idea. Now, it really helps to work through examples, and there's lots of examples to try. Again, make sure you're checking the other video. It will give you a really good intuition about what's going on. So what we need to show is that this process, this algorithm, always terminates. So we can always end up resolving conflicts and be done. So how do we know that we're going to actually stop? Well, we're going to make use of a very powerful tool. In other words, we're going to play one of our best cards that we have. Boom! Yes, the finite card. Now this is a powerful card. Lots and lots of good things come with it. Now, what's great about the finite card? Well, there's a couple of nice things going for it. It says, since I only have finitely many things, because this is a n by n board that we're thinking about, there's only finitely many places you can go. If I were to keep going forever and ever, I'd have to start repeating. So there must be a repetition of something. The other thing, so there's a second part, is that it's well ordered in some sense in this process, right? There's going to be this, followed by that, which means that if something does happen, like I were to revisit a place, there has to be a first time that it happens. So, okay, so our finite, we're going to use two things, that we have to visit something again, and we're also going to use that there has to be a first time that we visit that place. Okay, so what's the thing that we want to focus on? So we're going to focus on columns. That's going to be our key that we're going to go off of. So we're going to say, okay, we're placing the rook down, and we keep track of the columns. Which columns have we actually seen? And in particular, we want to say, okay, great. There will be a first time that we repeat a column. So in other words, what I mean by that is not necessarily the first time that we see two rooks in the same column, because when we start placing rooks, there's already there's already rooks on the board. And so what I mean is that when we are resolving a series of conflicts, we're going to say, okay, all right, have we seen that column before when we tried to resolve? And we're going to say, okay, it will have to happen eventually because there's only finitely many columns. And there'll be a first time that happens. Now you might say, well, wait, what if there's no repetition? It resolves, everything's great. And we're like, fantastic. See, that's not the part we have to worry about. We have to worry about when it doesn't resolve. So that's what we're going to focus on. Okay, so again, we're going to be focusing on columns. How have we seen the columns? Which columns have we used? Which columns haven't we used? And look for the first time that we repeat a column. We're going to assume that we're in a process where it doesn't stop, which means we have to have a repeating column. All right, so this one is going to take a little bit for us to go through, but mostly it's a little bit of notation and just say, hey, let's follow the process along until we hit that first time that we've seen a column again. So what's the notation? Whenever we see R with a subscript, that says, oh, that's the row that we're seeing at some stage. So R for row. A is the value of the cell. In other words, it's what the rook is covering. So that's what A corresponds to. Now the nice thing is if I know R, which is what row I'm in, and I know A, what value I want to cover, I also know the column. That's uniquely determined. And it's a nice relationship. Namely, you add those two numbers together, and you take things modulo n. So everything is done modulo n. That's why you'll notice there's these 3 lines. 3 lines means equivalent modulo n. You can think of it basically like addition. All right, so keep that in mind. R for rows, A for the value you're covering, A plus R is your column. Now, when we begin placing rooks, we're going to say, okay, there's 2 rows not yet used. So those are going to be called R0 and R1. And the first rook, right, because we're going to start by putting a rook down, we're going to say, what do we want to cover? Well, that's going to be A1. All right, so the process begins. We say, great. We put the rook down, and we say, where is it? Which column is it in? Well, it's in A1 plus R0. Now, we're going to assume that we don't stop, which means that there's a conflict. Okay, that means that there's another rook in some row, and we'll label that row R2, and covering some cell, we'll call that A2. All right, well, great. These two are in the same column. So, what do? Well, we need to resolve the conflict. And we resolve the conflict by we take this rook, this new rook here, and we move it. Now, it's still going to cover the same value, but it moves into the next row, which is R1. So we have A2 plus R1. So that's where the rook moves to. In particular, the column it moves into. And again, we say, conflict. Lots of conflicts going on here. So it's going to be the same column as some other rook, which we'll say is in some row R3 and some label A3. We say, okay, great. Now we take this rook and we relocate. So we say, okay, where does it go to? Well, same value, and now it's going to go into R2. Well, why R2? Well, see, R2 got freed up back here. So say, okay, great, move that into that freed up row. And we repeat. I say, another conflict, and so forth, and so forth, and so forth. And we're, so far, every single time that we've seen a column, it's like the first time that we've ever seen that column. That's important. Remember, we want to keep track. Every one of these is the first time we've seen a column until eventually we reach some point, and when we resolve that conflict, so this is after t iterations, you can think of it, we say, wait a second, when we move that rook to its new column, it's a column that we saw before. So here, S and T are sort of different steps in the process. And it doesn't have to be that S is 0, because it's not that we're claiming it forms a loop, we're just claiming it sort of comes back on itself. So it could be like a number 6, right? So you start here, and then it comes back and says, I've seen that before. It doesn't have to be the start where I saw it before, but I saw it before somewhere. All right, so this is essentially just capturing the process of moving the rooks. So the nice thing is we have these beautiful equations where we say, okay, the conflicting rooks, and then we have this last equation that says, we've seen this before. So what we want to do now is put all this together and see what we get. So here we have all the equations put into one place. And really, there's sort of two sets. And it's important to understand what these two sets are. So most of them fall into our first set, which says, hey, we have conflicting rooks. And then there's this last equation that says, and we've seen this one before. Remember, this is the first time that we've seen it. That's important. So we haven't seen any repeats before this stage. All right, now let's take a look at what we have. We have a whole bunch of equations. And so what we can do is we can compare them and say, well, what do we get when we put them all together? All right, well, what do we see? Let's start with the A's. Notice over here we have AS through AT. All right, well, that's fine. And now you say, hey, look, if I put AS here, and then that would be AS plus 1 through AT, so these are going to match, which is great. Okay, so in essence, the sets of labels all line up. Perfect, perfect. Well, do we have anything else that's kind of similar? Well, let's look at the rows, right? The location of the rows. And let's see what we have that can line up. Well, notice here we have row S plus 1 through row T minus 1. Okay, well, that's the same as right over here. So row S plus 1 through row T minus 1. And we have these rows for S minus 1. All right, great. So now we say, aha, these match as well. So you might say, wait, are we done? Have we matched everything? Well, there's still 2 pieces left. And this is the important part. We say, let's look at these 2 parts. Well, what's left? Well, what's left is that row and that row, which means since we have all these equations put together, we must come to the conclusion that these also must match. When I talk about match, just put it in collectively all together. So our conclusion, row S is the same as row T. In other words, when we talk about the labeling, the row that we label at the iteration for S has to match the row that we labeled for the iteration for T. And we're like, aha, we did something, right? What? What did we do? So we need to think about, why is this so bad? Where's our contradiction lying? Because we have to come to the conclusion that, wait a second, hold on, we can't have that happen. That's impossible. So let's take a second to sort of follow the process along and say, oh, because I know that what I'm calling row at the S step is the same as row at the T step, that's going to lead to something which is impossible. So let's start where this process started at the loop, right? Because we said, there's this loop where we come back and see something for the first time. So when we started, we said, okay, well, what's happening is I have this row. And in particular, it's row labeled S minus 1, and there was a rook there. Okay, and we moved that rook in, and we said, uh-oh, conflict. Now, because of our notation, where was the conflict going to be at? Well, the conflict was going to be up in what we were labeling as row S plus 1. Okay, so in other words, there was a rook here. Okay, well, what do? Well, we move it. That rook needs to be moved. So we pick it up and we move it. Where does it move to? And the answer is it would move into what we are calling row S. Okay, so there the rook moves. All right. Now, after you put this rook down, what happens? Well, okay, you see that there's going to be something that it's going to conflict with, because we're sort of in this sort of infinite loop. So there's some row, I'll call row, it's now S plus 2, as we follow along with our scripts here. Say, hey, look, there's a conflict here that needs to move. So that moves somewhere. I don't know. And we keep going, we keep going, until the very last part before we hit the repeat. So to recap, we're now to here, this part. So we started somewhere back here in the dot, 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 and we came to here. And what does that tell us? Well, what that tells us is that we have the situation where, let me grab a new color here. I have some row, I don't know, let's say it's up here. Okay, so here's a row, and it's row T minus 2. Now, I'm going to be careful here before I put any rooks down, because what does the situation tell us? Well, it tells us the following, that when I look at that rook in that row T minus 2, and I say, okay, it covers some cell, it conflicts with the rook that we're labeling row T. What do we know about that row? We know that that's the same as the row labeled S. So these rooks, that's going to say, look, it has to conflict with something in row S. Now, there's two possibilities. Now, we'll say, okay, the one possibility is that this rook hasn't moved. Okay, if that rook hasn't moved, then that would be the picture of the conflict. All right, now we're saying, aha, why is that bad? Well, how many conflicts have we seen in that column? We saw one for the first time we placed something in that row S, and then we saw a second one for this one that got moved into that row, what we're calling T minus 2. Now, why is that bad? Remember, that's two conflicts in the same column, which means that we shouldn't see that before what? Well, we shouldn't see that too soon, because that says we've repeated a column at this stage. But we aren't supposed to repeat a column until the next step. So what happened is we said, okay, the first time that we saw a repeated column wasn't actually the first time. Something happened before. But wait a second. You can't be before the first time. Impossible. Impossible. So that's our contradiction, right? We said, something had to happen first. And we said, okay, follow that through and said, actually, it happened before the first time. Well, you can't have that happen. All right, now you might be saying, Steve, that's all well and good. But what if this rook had moved? Okay, we still win. How can a rook move? By the algorithm, the only way a rook can move is if it's conflicting with something in the same column, and therefore there would have been a conflict in that column again. So even if that rook weren't there, there would still be two times that we see something in that column. So that's why it has to be the case that, nope, okay, it has to stop. In fact, we've really shown something a little bit stronger. We said, hey, we really can't repeat any columns. So when we go through placing these rooks, we'll never use a column more than once in each round of our rook placement. Now you might say, well, hey, hold on a second. In order for this procedure to work, you have to have those free rows to move into. And when you put the last rook down, there's no freedom because you don't have two free rows to work with. In fact, you really don't have much of anything to work with. You only have one possible place it can go. Now, why? Well, if you think about a board, if it's an n by n board, if I've placed n minus 1 rooks, that means I've covered n minus 1 of the columns, and I've covered n minus 1 of the rows. And you say, oh, well, look, there's just one little piece there that hasn't yet been covered because there's only one column it could go in and only one row it could go in. So there's just this one candidate. And so now we say, okay, how do we know we're going to be safe? We put that rook down, no problems. Everybody's happy. All right. Well, so this is not too bad. There's sort of two things in play. The first thing goes back to one of the things we learned about when we started talking about these rook placements, which is if we have a full rook placement, so we cover n cells, no two rooks in the same row, no two rooks in the same column, and we add up the values that are covered, it has to be something that's equivalent to n. Well, I should say equivalent to 0 modulo n. It's a multiple of n. And so we say, great. So now we know we've placed the first n minus 1 value. So we know we have something covering a label A1, something covering something with a label A2, all the way up through an minus 1, and then the question mark. And when I talk about the question mark, I mean, hey, what's on that cell? That's the question. Okay, so I know it's a multiple of n, which really means it's the same as 0 when we do modular arithmetic. So 0 mod n. Now, when you go to the Hall's Juggling Theorem, there's an assumption made about these numbers. Namely, they aren't arbitrary. If you look at their average, it's a whole number, which means that if you add all the numbers up, well, lo and behold, that's a multiple of n. That's the only way you can get the average to be a whole number. So again, by our assumptions, the sum a1 up through an is the same as 0. And now we say, oh, cancel, 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 cancel. And we come to the very happy conclusion, aha, the last cell is exactly what we want to put in. So that means that when we put that last rook in, even though there's only one place for it to go, it's going to sit in perfectly. And it's going to be like, ah, just the way it wants. So all our rooks now have succeeded. We've put down everything. Good to go. Good to go. One of the things that you often look at when you have an algorithm is you say, okay, great. I have this lovely algorithm. How fast is it? In other words, how many steps do I have to take to run before I reach the end? Because, you can have two algorithms that have the same output, but one might take much, much, much longer, So it's not just a matter of, do I get the right answer? Do I get it relatively efficiently? And so we can say, okay, in this case, you get things which are not so bad. Because if you think about how many rearrangements there are that are potential ones to look at, it's n factorial. That's a lot. And we don't want to have to go through and check all of them because n factorial grows pretty big with n. But the good news is our proof really says, hey, every time that we are working on resolving that conflict with a new rook that we're adding to the board, we only use each column at most once. Now, this is great because if I have, k rooks already placed, there's only k possible times I might have to move things around. So in particular, if we think about the bumps, how many times we have to make an adjustment, well, when you place the first rook, no problem. That's great. When you place your second rook, well, you may have to make one modification, one adjustment. When you place your third rook, you may have to do two. Your fourth rook may have to be 3, all the way up to the very penultimate case. When you place your n-1th rook, maybe you need to do n-2 bumps. Well, worst case scenario. And the last one, no problems. Life is good. So we have a bound. So the number of bumps you need is at most the sum of what you see here. And this is an upper bound. I'm not claiming that this is the truth. I'm just saying, let's just do some really back of the envelope computations here. Say, hey, you never need to bump more than 1 plus 2 plus 3 plus n, all the way to n-2. Well, we've seen these kinds of numbers before. These are triangular numbers. We know how to add these up. So we get n-1 choose 2, and that is less than half n squared, just throwing out lower order terms. Okay, so like n squared over 2, that's about, for algorithms like this, that's actually pretty reasonable. You can get through conflicts fairly quickly, n equals 1,000. Yeah, sure, you can do that. No problem. No problem. Now we talked about, okay, here's a bound, but now you can say, okay, hold on. What actually happens? What does the data say? We do have some data. And so it turns out that a half n squared is kind of a bit generous, it looks like. We don't know what the right answer is. And honestly, all the data that we have is here in this page, which is not very much. So, for instance, at 3 and 4, okay, it is what we think it is. But even starting at 5, we don't get to 6. Nothing takes more than 5. And what takes 5? Well, it turns out that for all intents and purposes, just one kind of pattern takes 5 bumps. This 0, 2, 1, 0, 2. So if you were to feed that through the algorithm, you'd have to move things 5 times. 5 corrections would have to be made. Well, 6, you need 8 at most, 7, 13, 8, 18, 9, 24, 10, 30, 11, 37. And again, here, this is the pattern that you feed into the procedure. 1, 0, 1, 9, 7, 10, 0, 10, 0, 0, 6. You feed that in, it'll take you 37 corrections for it to work out, which, not so bad. Now, you might be saying, okay, what happens for other cases? We don't know. For 12, we don't have all the data. We do know patterns that take at least 42. Is that the answer? Maybe. Maybe there's some that take more. We don't know. You might also notice that there's stars here. What do they mean? Well, the stars indicate the times when really, essentially it says like, this is the worst case scenario. For all intents and purposes, it's unique. So, in other words, not only say at 11, does this thing take 37 modifications, it's only this that takes 37. So everything else takes fewer. Yet for 10, there's actually multiple patterns that take 30 modifications. Why? I don't know. It's fun to not know things. It makes life more interesting because that lets us keep exploring, keep looking for new things. And I think there's still a lot of good, interesting math to be done here. All right, now we have a good idea of the why things work for Hall's theorem, and we know how to use it, so good. We have a beautiful, clean result. All right, done.